On February 20th, 1844, in the midst of a carnival ball in Vienna, Ludwig Eduard Boltzmann entered the world. His birth during the festivities of Mardi Gras seemed almost prophetic, a life that would be marked by extreme highs and devastating lows, brilliance and darkness, celebration and despair. Born into a family of modest means, his father was a tax official. Young Ludwig showed no obvious signs of the genius that would later emerge. But Vienna in the mid-19th century was a city of transformation, caught between the old aristocratic order and the new scientific age, and Boltzmann would become one of the bridges between these worlds. Tragedy struck early. When Ludwig was just 15 years old, his father died, leaving the family in difficult financial circumstances. His mother struggled to maintain their middle-class respectability, but there was little money for luxuries. What they did have was ambition for their son and an understanding that education was the path forward. Young Boltzmann was a serious student, though not particularly distinguished in his early years. He was nearsighted to the point of near blindness without his thick glasses, suffered from asthma, and was plagued by headaches that would torment him throughout his life. Physically, he was not imposing, of medium height, with a round face and an increasingly round body as he aged. But behind those thick spectacles was a mind beginning to perceive patterns in nature that no one else could see. In 1863, at age 19, Boltzmann enrolled at the University of Vienna to study physics and mathematics. This was fortunate timing. The university was home to Joseph Stefan, one of the leading experimental physicists of the era, who would become Boltzmann's mentor, patron, and lifelong friend. Stefan recognized something in the awkward young student, a gift for mathematical physics, an ability to see the deep structure underlying physical phenomena. Under Stefan's guidance, Boltzmann flourished. He devoured the works of James Clerk Maxwell, whose kinetic theory of gases suggested that the properties of gases could be understood by treating them as vast collections of moving particles. This idea, that macroscopic properties emerge from microscopic behavior, would become the obsession of Boltzmann's life. Boltzmann received his doctorate in 1866 at age 22 with a dissertation on the kinetic theory of gases. It was competent work, but not yet revolutionary. He was still learning his craft, still finding his voice, but the seeds were planted. He became Stefan's assistant, and the two worked together on problems of radiation and thermodynamics. In these early years, Boltzmann was happy, productive, surrounded by supportive colleagues. He couldn't know that he was laying the groundwork for a scientific revolution, or that this revolution would eventually consume him. The battles that would define his later life, the fights over atoms, over probability, over the very nature of reality, were still in the future. For now, he was simply a promising young physicist, working in relative obscurity, trying to understand how heat and motion were related at the deepest level. In the 1870s, Boltzmann began the work that would make him immortal. The problem he tackled was deceptively simple. What is heat? By the mid-19th century, scientists knew that heat was related to molecular motion. Hotter objects have faster-moving molecules. But how exactly did this microscopic chaos produce the orderly laws of thermodynamics? The second law of thermodynamics stated that entropy, roughly, disorder, always increases in isolated systems. But why? What fundamental principle of nature guaranteed this? Boltzmann's insight was to approach the problem statistically. Imagine a gas in a box, he said, composed of countless molecules bouncing around randomly. At any given instant, the molecules have some particular arrangement, some distribution of positions and velocities. Now, some arrangements are more probable than others. A state where all the fast molecules are on one side and all the slow molecules on the other is possible, but incredibly unlikely. A state where fast and slow molecules are evenly mixed is far more probable, simply because there are vastly more ways to arrange the molecules to achieve mixing than to achieve separation. Boltzmann realized that entropy was really a measure of probability. High entropy states are high probability states, and the second law of thermodynamics simply reflects the fact that systems naturally evolve from less probable to more probable configurations. This was revolutionary. Boltzmann had reduced a fundamental law of nature, the irreversible increase of entropy, to statistics, to probability, to counting. In 1872, he published his H-theorem, which attempted to prove mathematically that entropy must increase over time. The proof relied on a clever mathematical function, which he called H, related to entropy, and showed that for a gas of colliding molecules, H would always decrease, meaning entropy would always increase. It seemed he had derived irreversibility from reversible microscopic laws, had shown why time has an arrow, why scrambled eggs don't unscramble. But there was a problem, and Boltzmann's colleagues were quick to point it out. The microscopic laws of physics, Newton's laws of motion, are time reversible. If you filmed molecules colliding and played the film backward, you'd see perfectly valid physics. So how could time irreversible behavior, entropy increase, emerge from time reversible laws? This was the reversibility objection raised by his colleague Joseph Loschmidt. And there was another problem. Poincaré's recurrence theorem proved that any isolated system must eventually return arbitrarily close to its initial state. So entropy couldn't always increase. Eventually, it must decrease as the system returns to lower entropy configurations. These weren't just technical quibbles, they struck at the heart of Boltzmann's approach. Boltzmann's response was profound. He conceded that yes, entropy could decrease, but only with incredibly tiny probability. Yes, the scrambled egg could spontaneously unscramble, the mixed gases could spontaneously separate, but the waiting time would be incomprehensibly long, far longer than the age of the universe. The second law wasn't absolute, it was statistical. It held not because entropy must always increase, but because entropy almost always increases. This probabilistic view of natural law was deeply unsettling to many of his contemporaries. They wanted certainty, absolute laws, deterministic guarantees. Boltzmann was offering them probability and statistics. In 1877, he published his most famous result, the equation relating entropy S to the number of microscopic states W, written as S equals K log W, where K is now called Boltzmann's constant. This equation, eventually carved on his tombstone, is the foundation of statistical mechanics, the bridge between the microscopic and macroscopic worlds. But Boltzmann's statistical approach rested on a controversial assumption, that matter is composed of atoms. Today, this seems obvious, uncontroversial, the kind of fact we learn in elementary school. But in the late 19th century, the existence of atoms was hotly debated. No one had seen an atom. No direct evidence proved they existed. And influential scientists, particularly the energeticists and positivists led by Ernst Mach and Wilhelm Ostwald, argued that atoms were unnecessary metaphysical speculation. Science, they insisted, should deal only with observable quantities like energy and temperature, not hypothetical invisible particles. The debate came to a head at the 1895 meeting of the German Association of Scientists and Physicians in Lübeck. Ostwald gave a lecture attacking the atomic theory, arguing that all of physics could and should be reformulated in terms of energy alone, without reference to atoms or molecules. Boltzmann, who had traveled from Vienna to attend, rose to defend atomism. The confrontation was intense, almost personal. Boltzmann argued passionately that atoms were not just useful fictions but real entities, that the success of kinetic theory and statistical mechanics provided overwhelming indirect evidence for their existence. But Ostwald was unmoved, and he had powerful allies. Mach, one of the most influential physicists and philosophers of the era, had made his opposition to atomism a central part of his positivist philosophy. For Boltzmann, this wasn't just an academic debate, it was personal, existential. His entire life's work rested on the reality of atoms. If atoms didn't exist, then statistical mechanics was just a mathematical game, elegant perhaps, but ultimately meaningless. And the attacks kept coming. Critics pointed out apparent contradictions in his work, challenged his mathematical derivations, questioned his assumptions. Boltzmann defended himself vigorously, publishing paper after paper, refining his arguments, addressing objections. But the battle was taking its toll. He was spending more energy defending old work than creating new work, and he was increasingly isolated. Many younger physicists were moving in other directions, toward electromagnetism, toward the emerging puzzles that would soon birth quantum mechanics and relativity. Boltzmann's personal life became increasingly difficult. In 1876, he had married Henriette von Agentler, a young woman he had met while teaching. They would have 5 children together, and by all accounts, Henriette was devoted to him, supportive and loving. But Boltzmann's mental health was deteriorating. He had always been prone to mood swings, periods of manic productivity followed by deep depressions. The controversies over his work made things worse. He suffered from severe headaches, insomnia, and what we would now recognize as bipolar disorder. There were periods when he couldn't work, couldn't function, when the darkness was overwhelming. He moved restlessly between academic positions, Graz, Vienna, Munich, Leipzig, back to Vienna, never quite finding peace, always hoping the next position would bring relief. His colleagues noticed his suffering, but mental illness in that era was poorly understood and deeply stigmatized. Boltzmann struggled on, teaching, writing, fighting his battles, both scientific and personal. What made Boltzmann's situation even more difficult was that he was fighting on 2 fronts. He wasn't just a physicist. He was a philosopher of science, deeply engaged with questions about the nature of scientific knowledge, the relationship between theory and reality, the role of models and hypotheses in physics. And here, too, he found himself in opposition to the dominant trends of his time. The positivists, led by Mach, argued that science should restrict itself to describing observable phenomena, avoiding metaphysical speculation about unobservable entities like atoms. Theories, in this view, were just economical summaries of experience, useful tools but not descriptions of reality. Boltzmann rejected this utterly. For him, atoms were real, not just useful fictions. Theories were attempts to describe an objective reality that existed independently of our observations. This put him at odds with the positivist philosophy that dominated late 19th century science. He even took over Mach's chair of philosophy at the University of Vienna in 1902, after Mach retired due to ill health, an ironic twist given their philosophical disagreements. Boltzmann used this position to argue for a realist view of science, insisting that we should believe in the reality of the entities postulated by our best theories, even if we can't directly observe them. But Boltzmann's philosophical views were more nuanced than simple realism. He understood that scientific theories are models, simplifications that capture some aspects of reality while ignoring others. He appreciated that different models might be useful for different purposes, that a theory could be valuable even if not perfectly true. In his lectures, he emphasized the importance of pictures and mechanical models in physics, not because they were literal descriptions of reality, but because they helped physicists develop intuition and make predictions. This pragmatic streak in his thinking, combined with his realism about atoms, created a complex philosophical position that didn't fit neatly into the categories of his time. His teaching was legendary. Students remembered him as passionate, engaging, sometimes rambling, but always illuminating. He didn't just present results. He showed how to think, how to approach problems, how to build physical intuition. He taught courses not just on physics, but on the philosophy of science, on the history of mechanics, on the methods of theoretical physics. He wrote textbooks that were models of clarity and depth. Yet he felt increasingly marginalized in the physics community, increasingly out of step with younger colleagues who saw his focus on mechanical models and atomic hypotheses as old-fashioned. The new generation was embracing field theories, electromagnetic waves, and the strange puzzles emerging from blackbody radiation and spectroscopy, problems that would soon explode into quantum mechanics. Boltzmann's statistical mechanics would prove essential to understanding these phenomena, but he didn't live to see it vindicated. His lectures sometimes revealed his dark humor and self-awareness. He would joke about his unpopular opinions, about his battles with critics, about the loneliness of holding views that others rejected. But beneath the humor was real pain. He was a man who had devoted his life to understanding nature at its deepest level, who had made contributions of lasting importance, and yet found himself fighting rearguard actions, defending basic assumptions that he thought should be obvious. The stress was immense, unrelenting. and his mental health continued to deteriorate despite Henriette's constant care and support. By the early 1900s, Boltzmann was in his late 50s and early 60s, internationally recognized but increasingly tormented. The controversy over atoms continued, though it was beginning to shift in his favor as new experimental evidence accumulated. In 1905, though Boltzmann wouldn't fully appreciate it, Einstein published his paper on Brownian motion, showing how the random jiggling of pollen grains in water could be explained by collisions with invisible water molecules. This paper provided some of the most direct evidence yet for atoms, and it relied heavily on the statistical methods Boltzmann had pioneered. Jean Perrin would later perform experiments confirming Einstein's predictions, providing near-conclusive proof of atomic reality. Boltzmann's view was being vindicated, but he was too deep in his own darkness to fully appreciate it. His depression was worsening. The headaches were more frequent and severe. His eyesight, never good, was deteriorating further. He had difficulty sleeping. Colleagues reported that he would sometimes lecture brilliantly, with all his old energy and insight, but then sink into black moods where he doubted everything he'd done, everything he'd believed. The cycling between mania and depression, the hallmark of bipolar disorder, was becoming more extreme. He tried various treatments, nothing worked. His wife and children did what they could, but mental illness on this scale was beyond what 19th-century medicine could address. There were no effective treatments, no antidepressants, no lithium. There was just suffering and the attempt to endure. In summer 1906, Boltzmann traveled with his family to Duino, near Trieste on the Adriatic coast, for a vacation. They stayed at a hotel, and Boltzmann seemed to be enjoying the sea air, the break from Vienna. Henriette and the children went to the beach on the afternoon of September 5th. Boltzmann said he didn't feel well and stayed at the hotel. He was alone in their room. And there, at age 62, Ludwig Boltzmann hanged himself. When his daughter returned to the room, she found him dead. The news shocked the scientific world. Tributes poured in from colleagues across Europe, many of whom had sparred with Boltzmann over the years but recognized his brilliance. They spoke of his contributions to physics, his insights into the nature of entropy and probability, his pioneering work in statistical mechanics. But they also acknowledged, often indirectly, the personal struggles he had endured, the controversies, the isolation, the mental torment. Some blamed the attacks on his work for his death, though this is almost certainly too simple. Depression and bipolar disorder are illnesses with biological roots, not simply reactions to external circumstances. But the controversies surely didn't help, and the sense that his life's work was under constant attack must have deepened his despair. He was buried in the Zentralfriedhof, Vienna's central cemetery, in the same city where he had been born 62 years earlier. On his tombstone, his family had inscribed the equation S equals K log W, the mathematical expression of his greatest achievement, the formula connecting the microscopic and macroscopic worlds, the foundation of statistical mechanics. It was a fitting memorial for a man who had seen deeper into the nature of heat, probability, and entropy than anyone before him. But it was also unbearably sad, a life of genius ending in suicide, a mind that had unlocked secrets of nature, unable to find peace in itself. The tragedy of Boltzmann's death is compounded by how quickly his ideas were vindicated. Within a few years, the atomic hypothesis he had championed was universally accepted. Einstein's work on Brownian motion in 1905, Perrin's experiments between 1908 and 1913, and the emerging field of quantum mechanics all provided overwhelming evidence for the atomic nature of matter. Even Ostwald, one of Boltzmann's chief opponents, eventually conceded that atoms were real. The battle Boltzmann had fought so long and so painfully was won, but he wasn't there to see it. More than that, Boltzmann's statistical mechanics became one of the cornerstones of modern physics. When Max Planck derived his blackbody radiation formula in 1900, the result that launched quantum mechanics, he used statistical methods directly inspired by Boltzmann. When Einstein, Bose, Fermi, and Dirac developed quantum statistics in the 1920s, they built on Boltzmann's foundations. The entire field of thermodynamics was reformulated in terms of statistical mechanics, exactly as Boltzmann had envisioned. His equation S equals k log W became one of the most important equations in all of physics, as fundamental as E equals mc squared or F equals m times A. The applications are everywhere. Every time we calculate the entropy of a system, we're using Boltzmann's insights. Every time we understand why heat flows from hot to cold, why gases mix irreversibly, why time has an arrow, we're implicitly invoking Boltzmann's statistical interpretation. Statistical mechanics underlies our understanding of materials, of chemical reactions, of black holes, of the early universe. The constant K that appears in Boltzmann's equation, Boltzmann's constant, appears throughout physics and chemistry, connecting temperature to energy at the molecular level. It's one of the fundamental constants of nature, like the speed of light or Planck's constant. But Boltzmann's legacy goes beyond specific equations or techniques. He changed how we think about physical law. Before Boltzmann, laws of physics were thought to be exact, deterministic, absolute. Boltzmann showed us that some laws, particularly the second law of thermodynamics, are statistical, probabilistic, emergent from the microscopic chaos of countless particles. This was a profound shift in perspective, one that prepared the way for the probabilistic nature of quantum mechanics and the statistical description of complex systems. In this sense, Boltzmann was ahead of his time, grasping truths about nature that his contemporaries weren't ready to accept. His philosophical contributions also endured. His pragmatic realism, the view that we should believe in atoms because atomic theory works, not because we can directly observe atoms, became increasingly influential. As physics moved toward ever more abstract theories in the 20th century, Boltzmann's emphasis on the importance of models, on the creative role of imagination in science, on the need to balance mathematical rigor with physical intuition, remained relevant. He understood that physics is not just mathematics and not just experiment, but a creative synthesis of both, guided by intuition and constrained by reality. The human tragedy of Boltzmann's life, the brilliant mind tormented by doubt and depression, the revolutionary thinker who died believing his work was in vain, casts a long shadow. It reminds us that scientific progress is made by human beings, with all their frailties and struggles. It reminds us of the cost of being ahead of your time, of fighting battles against entrenched opposition, of defending ideas that seem obvious in retrospect, but were controversial when first proposed. And it reminds us that genius offers no protection against mental illness, that the same qualities of mind that enable great insights can also bring great suffering. Today, when students learn statistical mechanics, they often don't know the full story of the man who created it. They learn the equations, solve the problems, apply the methods, but they might not know about Boltzmann's battles with the anti-atomists, his philosophical struggles, his mental illness, his tragic end. They see the clean, finished product, the beautiful mathematical framework, but not the messy, painful process by which it was created and defended. Yet understanding that process, understanding Boltzmann's life in all its complexity, deepens our appreciation not just of statistical mechanics, but of science itself. Science is a human endeavor, and its history is full of human stories, of triumph and tragedy, of insight and struggle, of ideas fought for and lives given meaning or torn apart by the pursuit of truth. Ludwig Boltzmann gave us the tools to understand entropy, probability, and the statistical nature of thermodynamic law. He showed us why time has an arrow, why scrambled eggs don't unscramble, why the universe evolves from order to disorder. He connected the microscopic world of atoms to the macroscopic world of everyday experience. And he did all this in the face of intense opposition, at great personal cost, driven by a conviction that atoms were real and that their statistical behavior held the key to understanding nature. His equation stands on his gravestone in Vienna, a testament to a life devoted to uncovering nature's secrets. The tragedy is that he didn't live to see how completely, how triumphantly, his vision would be vindicated. But the vindication came nonetheless, and his legacy endures in every physics textbook, in every application of statistical mechanics, in every atom whose reality we no longer question. Ludwig Boltzmann's battle is over, but his ideas live on, fundamental to how we understand the physical world.